So today I'm going to talk about homogeneous unit sliding mode control. Here is a brief outline of the talk. So after some brief introduction, I will present a short some small elements of homogeneity theory, and next we will try to understand how these elements may help us to improve the design of so-called unit control or unit sliding mode control, which is very well known for many years. So here I give some historical remarks about sliding mode control theory. It's a very old story. It started from 1930s. Next, it was some mathematical background discovered in order to justify some derivations from this very first attempts to study sliding mode systems which had sliding modes. For example, the notion of sliding mode was introduced in 1937, for example. But let's say the sliding mode control theory anyway started after the Second World War. There are a few papers referred here where some points of derivations in the sliding mode control theory, and one of them here is mentioned as a so-called unit sliding mode control, unit control short. So it was presented first at the conference, for example, in 1974, I think it was a CDC where it was presented, and next it was a paper in IEEE. And since then, let's say the methodology for this unit sliding mode control was not modified. So it is very classical approach. So if you consider, for example, this linear system, and we have a plant with a matrix A, which is assumed to be known, B matrix is also known. We have possibly some perturbations, but there is a matched perturbation, the typical assumption for sliding mode control design. And we assume that this perturbation gamma is bound. So the usual goal for the sliding mode control design is to select some feedback which guarantees that some output will be globally uniformly finite time stable. You can say this on the modern language, which means that if we select some, for example, linear surface, Cx equals 0, our controller should guarantee that this surface will be reached in a finite time, and next all trajectories will slide on this surface. And the conventional assumption to design such a controller as a unit control, is that the dimension of the sliding surface and the matrix B, the matrix of the control inputs, should be consistent in some sense, so that we must have this parameter P, the number of equations which define sliding surface, must be less or equal to the number of inputs. And in fact, for the design, it is usually necessary to be equal, because next, for the design, we usually assume that matrix CB is invertible. If this matrix CB is invertible, then the control traditionally designed is the following way. This is the formula is just a straightforward consequence of the unit control proposed by Gutmann and Leitman. Why it works? Let's try to understand, because next it was some specific selection of parameter. This is in fact a scalar parameter K. And some strange linear term here. I just want to note also that why it is called unit control is just because of this term. This term ensures the slide mode is a discontinuous term. It's a division of the vector sigma by its norm. So norm of this vector is 1. It's a unit vector. That is why this is a unit control. Why this control solve the problem of this uniform finite time stabilization of the output sigma. So we should consider, to understand this, we should consider the dynamics of the output, and this is easy to compute. We just compute the derivative and substitute the equation for x dot, and we have the following representation. Now we have some term CAX here, And the selection of this term in the unit control is just in order to reject this term as linear. And next, after such a selection, we will have in the closed loop form the system which is not dependent on our variables, our parts of the state x, except with output signal. But the second term in the control is selected such that this output will be stable and asymptotically stable, and even more under some perturbation. So here, this part, the gain selected for the unit control, rejects this perturbation. It's easy to check this property. We may consider the usual sum weighted Euclidean normal quadratic function if you prefer for the system, and find that calculation of the time derivative of this Lyapunov function candidate along the trajectories of the system will give us just the estimate for the derivative which guarantees finite time convergence of the state sigma to 0. So we have that derivative of the norm is less than some constant minus rho. This term selected in the control just dominates with it. And we guarantee that after finite time, which can be estimated using the initial state of sigma, we have a sliding mode. So this is a very simple design. It's algebraic, very simple. Just we need to invert some metrics and select some gains rather easily. And we guarantee that we design the sliding mode controller for the selected surface sigma equals 0. But the assumption here in M is rather restrictive. So the question is how to try to relax this assumption. And the usual approach is, of course, higher order sliding mode control. And it gives us, it's not exactly unit control, but it gives some solutions how to design sliding mode controllers. Here are a few references about sliding mode control design for different cases when the surface is a rather specific surface, not for any surface C, but some cases at least. We can design the controller when P doesn't equals M, but the, let's say, dimension of the P of the sliding surface is inconsistent with the number of inputs. But the design of the higher order sliding mode control is rather trivial. Well, even in the case of single input system, you know that if, for example, the equations is rather big, for example, P greater than 2, and even if we select very specific sliding surface in order to guarantee what sliding mode control, higher order sliding mode can be designed, the analysis next is rather non-trivial. The functions for higher order sliding mode algorithms are not very difficult, not very simple. There's Professor Marina who is also participating in this seminar. And of course, if the number of inputs is increasing, then the story is even more. So in this talk, I will try to present you some ideas based on homogeneity, which may help to simplify the analysis and the design of the sliding mode controller. But next will be some issues in the implementation, but fortunately we solved easily recently, and we can use even some toolbox to implement. So the problem we are going to discuss is how to eliminate this restriction about surfaces and but preserve the simplicity of the design. And the key tool for this is a homogeneity. Homogeneity is in mathematics can be shortly formulated as a dilation symmetry. We know that by definition symmetry is some invariance of a mathematical object with respect to a group of transformations. For example, if we will use such a transformation like a rotation, for example, we will see that it doesn't change the size of the of the figure. So the size of the figure is invariant with respect to rotation, but it slightly changes the shape. Inversely, the dilation is a scaling or a zoom operation or transformation is preserves the shape of the figure, but changes its size. So we have an invariance of the shape of the figure with respect to dilation. Here is a simplest example of the dilation. Is a standard dilation when we take some vector from a vector space and multiply it by scalar. The homogeneity has very long story. The standard homogeneity has been introduced by Andrey and has been studied by Andrey 18th century. We can find homogeneity in the context of linear systems as one of properties of linearity. So if we have some linear mapping, by definition, this means that it is homogeneous, additive, and central limit. This is just a definition of linearity. This property is known as homogeneity in mathematics. But Leonard Euler introduced also a so-called homogeneity degree, which allows to analyze nonlinear functions using the same or symmetry of nonlinear function with respect to the same kind of operations. So if we take again a vector field, I do not specify here what is this vector field. It can be element from a Rn, it can be element from an abstract space, it can be even an operator. So if we have a operation multiplication by lambda, and for some function of x, we have the following symmetry property. It means scaling of the argument is equivalent to scaling of the value of the operator with the parameter lambda up to some power nu. And this power is known as a homogeneity degree. Here is a couple of simplest examples of homogeneous functions, like a linear function or quadratic function, and they have different degrees according to this definition of Euler. For quadratic, we have homogeneity degree 2, we have symmetry parameter nu equals 2, but for linear, for example, we have the same property for nu equals 1. Usually, if we have some symmetry of a mathematical object, then this symmetry is inherited by other objects induced by this original homogeneous object. So if you have a homogeneous function or homogeneous vector field, like here on the example, we have homogeneous ordinary ODE differential equation. It is linear. We have a symmetry of solutions of this or homogeneity of solutions. So if you see all solutions are symmetric, so if we know solution started from, for example, from this point with some initial condition, we just multiply by parameter lambda and we will have this solution. We will have a solution initiated in the inner port. The same you can observe, for example, for a homogeneous system of degree 0. So here you have an example of harmonic oscillator. This is an analog of harmonic oscillator. Continuous analogous relay oscillator, and you have the same kind of symmetry if you have homogeneity of the right hand side of some ODE. So homogeneity is inherited by other objects if you have a homogeneity of the function. The same you will have for derivative of the function. So if f is differentiable and homogeneous, then derivative will be differentiable. And the derivative will be homogeneous in the function. There is some famous homogeneous function theorem proven by Euler, which relates the derivatives and the function and its derivative. Here are a few analytic examples. What do we have in the case of symmetry or dilation symmetry or homogeneity of the function f? If f is homogeneous of degree 1 plus nu, for example, we have symmetry of the roots of the equation f x equals 0. So if we have one root, then multiplication by lambda this root, we will have another root. So for any homogeneous function, if we have one root, we have a space of roots. Of course, if x star is non-equal 0, but if x star is 0, then multiplication by scalar will just give the same element. The similar symmetry of solutions we have for homogeneous differential equations, and we have again this parameter nu here. So if we have simplest ODE, which is homogeneous, which right hand side is standard homogeneous, degree 1 plus nu, then this parameter nu plays an important role in the symmetry of solutions. So we can find explicitly the solution and discover the following property of this solution, but the scaling of the initial state with the parameter lambda will give us again the solution, which can be obtained by scaling of the original solution, multiplication by lambda, and scaling of the time. And the rule how this time will be scaled is defined by this parameter nu, which is obtained from the homogeneity degree. In fact, this property can be discovered for more generalized types of dilation, because this is the simplest case of dilation when we do multiplication by scalar. But dilation is a special family of transformations which have special topological characterizations. There are mathematical papers about this, how to define what does it mean a dilation, etc. And at least in the systems theory and stability analysis, the first paper devoted to analysis of differential equations which are homogeneous in a generalized sense was published by Vladimir Zubov in 1958, where he studied a special kind of dilation where he scales the state of the ODE non-uniformly. It is so-called anisotropic scaling. So if you have vector of states and you multiply each component of this vector by parameter lambda to some power R1, then you can define, then this will be a dilation if all these parameters are some positive values. In this case, this operation of scaling of the vector, which is for sure shortly it is denoted by lambda here, is the generalized dilation. The title of the generalized homogeneous differential equation. So it is the first generalization of the standard dilation. But this kind of generalization modifies slightly the definitions of the symmetry for functions and vector fields. They are different now, because if you consider some function h which maps Rn into R, then using this dilation operation, using this matrix lambda, the symmetry can be defined in the usual way like in Zubov. So the scaling of the argument is equivalent to multiplication of the value of the function by the parameter lambda to the power nu. But for the vector fields, in other words, for the right-hand sides of the differential equations, the symmetry with respect to this scaling operation lambda is slightly different. It is understood like a commutativity of two operators, operator f and the operator lambda, up to some scalar lambda to the power mu. So we can put lambda capital out of brackets up to multiplication by some scalar lambda to the power mu. And nu and mu here are homogeneity degrees. So it's the definition for the name for these parameters is the same in both cases, but you understand what we have a slight difference in the definitions and some collision when n equals 1, because mu is non-equal to nu. Mu is just in this case nu is just equals 1 plus mu. So on this stage we distinguish the notions of homogeneity for vector fields and for functions. It is just example which illustrates that using generalized dilation we can include in considerations larger class of systems. There are plenty of examples of generalized homogeneous systems. For example, this classical minimum time control problem when we need to stabilize in a minimum time system of some double integrator in a minimum time under some restriction on the control. The static feedback solving this problem is a sliding mode controller. The name for this kind of sliding mode controller is nested controller. And it is weighted homogeneous. You can easily check the dilation symmetry of the control and the dilation symmetry of the system. It's just a formal computation, and we see that this system is homogeneous of degree -1. That is why this kind of dilation and this kind of homogeneity degree like -1 frequently appears in the analysis of the high-order sliding mode controllers. If you look on papers of Professor Levanti, you can find in many considerations, even if it is not explained explicitly, in many considerations it is hidden with homogeneity-based design. A bit more, one more generalization of the dilation operation was presented by Matthias Kavsky. He suggested to consider as a dilation for the finite method Euclidean space the family of operations which satisfy the following two properties: group property and the limit property. So the family of operations D is dilation if we have the following property for these operations. This is just a mappings parent-parent. So the composition of two mappings is equivalent to dilation with just parameter. Geometrically, it can be easily explained, but if we have a vector x, we apply the first operator, we obtain new vector x, scale it one. And next, after the first dilation, we apply the second one. It is equivalent to application dilation with parameter s plus t. I recall that the dilation is here by definition is a one parameter family of operation. But the limit property just characterizes the class of these groups which are dilations, in fact, which by definition are dilations. It means that if we take the vector x, which is non-zero, and we tend the parameter s to -infinity, the norm of sx will go to 0, but if s goes to +infinity, the norm will go to +infinity. And in this talk, I will deal only with one particular case of this geometric dilation, the linear dilation. So if we will define our group T the following classical way, like exponential matrix, this antiguous generator, this matrix GD is known as generator of the dilation. Then I will have a linear dilation. In this case, I may cover all the particular cases of dilations, like standard, weighted, just considering the generators. Identity matrix, a diagonal matrix, linear correspond just to any antiguous matrix. Here is just illustrations, but they indeed different. In fact, this linear dilation corresponds to our previous considerations. We will replace lambda with a parameter e to the power s. Now the parameter of the group is just meant from R, but not from R+. It's not just positive parameter. Absolutely the same story, the same definitions, and in fact, we have even the same type of symmetries of solutions and so on. So we have many similar properties to the standard dilation, and even more in my book you can find a transformation coordinate which transform any linear homogeneous in the sense of linear dilation system to a standard homogeneous system. So they all are equivalent. But for design, it can be useful to deal with homogeneous with linear dilations. And first of all, what can we use for the design of for understanding of the geometry of the system with linear dilations. In fact, we know what the vector space is a set of operators with a set of vectors with two operations, vector addition and multiplication by scalar. We know for n multiplication by scalar is standard dilation with scalar is positive. Again, we construct a generalized some vector space Rn where multiplication by scalar will be replaced by a linear dilation. And in fact, we can construct such a vector space, but we need to introduce also a norm in this vector space. I recall here what the norm is just a continuous function satisfying three properties like positive definiteness, homogeneity, and triangle inequality. And we want to replace this standard homogeneity with generalized and construct a new norm. Such a new norm in the literature is known as homogeneous norm, but we will, for linear dilations, we consider a particular case of this homogeneous norm, which is defined implicitly in the following way. So if we have a dilation D and it is monotone with respect to this parameter. So if norm of D of S, X is the monotone function of S. Then we can define the so-called canonical homogeneous norm as a solution of the following algebraic equation. We fix X and find S of X such that this identity holds, and by definition we define the value of the norm in this way. So if D is a standard dilation, it's just exponent to the power minus S, we have what the usual norm coincide with the canonical homogeneous norm. And here is just geometric illustration and differences when we have, instead of standard dilation, we have a generalized dilation. So this is a level sets for the norm with a standard norm or ellipse. It's a weighted Euclidean norm, the unit level set is, and any level set of the norm is ellipsoid, and all the ellipsoids are in parallel due to the standard dilation with uniform scaling of ellipsoid. And in generalized case, we will have a scaling together, probably with some rotations and so on. So we will have non-uniform scaling of the unit level set canonical. We will use this object next for the design. It is rather simple. Next, the design based on this canonical homogeneous norm. It has many properties typical for the norm, but it's positive definite, it is continuous outside of the origin. If this canonical homogeneous norm is induced by weighted dilation, by some smooth outside of the origin norm, then canonical homogeneous norm is also differentiable and even has a rather simple representation for its derivative. So we can use this, despite that it is defined implicitly with strange objects, for the design of the for design analysis of control systems. In particular, we will use this canonical homogeneous norm as a Lyapunov function, exactly in the same way like we did this for the analysis of the unit control a few minutes before. And with such a canonical homogeneous norm, we can modify our space Rn to a generalized homogeneous Euclidean space where we change the rules for the summation and multiplication using this canonical homogeneous norm special homomorphism on Rn, and construct a new vector space in which we have different our rules for summation and multiplication by scalar, but in this vector space, this strange object we introduced before, this canonical homogeneous norm, is a norm in the usual sense. So we have all these properties typical for the norm, but in the sense of different operations, multiplication by scalar and summation. Why it is useful? Because before the design is rather similar to linear control, except the division, for unit control, except the division of the vector sigma, right? But with such of strange vector space, we can do the similar design, but let's say it will be linear in this vector space, but in the original vector space, it will be just some nonlinear controller which realizes the unit control. I would like to explain the basic idea based on stabilization of very simple linear system. And next we will adapt all these ideas to very quickly to homogeneous unit sliding mode control design. So let's consider the problem of homogeneous stabilization for the linear system. So we have a linear system without perturbations, nothing, it's just AB is known, control input as before is a vector, and we need to design a control U which stabilizes the system, the origin on the system asymptotically, such that the closed loop system is homogeneous of degree mu. It means after selection of our control, we must have the symmetry which I described at the beginning of my talk, but a scaling of the argument of the closed loop of the F for the closed loop system. Scaling of the argument is equivalent to scaling of its values up to some scalar. This is exactly the definition we discussed for the case of weighted dilation. But now D is just linear or something. In our type of general dilation, we will talk today only about linear dilations. So if we have the condition which you already seen before, if we have M equals N and matrix B is invertible, then this design can be based on the standard homogeneity. We can just select the control U in this form, one term which rejects linear part of the system, and another term which gives us homogeneity for the closed loop system of the desired degree. So with such a selection, we will have a standard in closed loop. We will have a standard homogeneous ODE. So if we will select the matrix K Gurwitz, we will have a stable system, because this is just a multiplication by scalar. You can check this using the standard quadratic. Stability, homogeneity is obvious. It's just scaling multiplication by scalar. This is a lambda. Now, multiplication by scalar here will give us exactly the identity we need. So it means that in the context of the standard homogeneity, we can have we might have we might design a global homogeneous stabilizer of the system. So the system closed loop system will be homogeneous of degree mu. And in fact, if the matrix A is non-zero, our controller, to make the system homogeneous, asymptotically stable and homogeneous of given degree mu, we need to reject this linear part if degree mu is non-zero, because linear system is standard homogeneous of degree 0 with respect to standard. But we need to have a closed loop, the system which will be homogeneous of degree mu, which may be non-zero in general case. In general case, this term must be somehow rejected, and in the case of standard homogeneity, it must be completely rejected if we want to have degree mu here non-equals 0. I recall you that mu equals -1 is a classical sliding mode controller case. We will have just x divided by norm x, and we will have a unit control. This means that for design of the unit control in the classical context, which is based on standard homogeneity, as we can see, we must completely reject this matrix AX during the design. The generalized homogeneity doesn't have this restrictive assumption. For example, if we will consider the single input system, and we will assume that the system already have some good form, like Brunovsky form of this form. It had a matrix. The pair B is controllable, had a special form, the matrix and the control. The matrix, in this case is a vector, has also a special form. Then we can just reject this part in the linear component of our system to have a system homogeneous of any degree mu, but with respect to weighted dilation. So if we select our controller in the following form, this form rejects just this line. See if we will have a closed loop system, I substitute my control U, I will have this form in my in closed loop, and the matrix A0 here just doesn't have this element. So we are rejecting. The second component is some homogeneous controller with respect to this weighted dilation. Dilation is selected in a very specific form, which is related of the structure of the matrix. We will next understand why this form is selected. And in this dilation, we just have special definitions of the scaling elements. So each component of the vector has to be scaled with different degree. So multiplication by lambda to a special power R1. This is the parameters. And with such a selection of dilation, the matrix is A0, which is non-zero matrix now. The matrix corresponds to the chain of integrators, controller chain of integrators. Yeah, and this matrix is homogeneous in the generalized sense. So taking any homogeneous controller, the closed loop system will be also homogeneous. There are many examples how to design some homogeneous controller for the system in this form. But this is a weighted dilation which is appropriate for single input system. For multi-input system, it can be designed, the similar type of controller can be designed by means of many transformations, but it can be also designed in a more simple way, just using linear dilation. But the dilation is non-uniform and has a special form related to the matrix of the system. But the key feature here for this design that after the selection of this term, the matrix A0 is called nilpotent matrix. So it may be non-zero matrix, but all its eigenvalues are zero. And in fact, it can be shown that for any controllable plant, even multi-input, we can always find some linear feedback, which will make the matrix nilpotent and appropriate in the closed loop form and appropriate next for implementation of globally homogeneous stabilizer. So here is just a basic idea how we are going to design our homogeneous unit control. So first we need to find some gain k which makes the matrix A plus bk, gain k0, which makes the matrix A bk0 homogeneous or nilpotent, in fact homogeneous with respect to some dilation generated by an anti-Gurwitz matrix GT, and the homogeneous of the required degree mu. And this generator, in fact, can be selected such that we have also homogeneity property for the matrix B for the control matrix. And next we design a homogeneous stabilizer for the already homogenized part. So for more story about this homogenization, I give here a few references where you can find these tricks with decompositions of the system or for linear dilation. And now we just implement this idea of homogenization plus some homogeneous control design to the design of this homogeneous unit control. The design is very similar to the design of the unit control, but under a bit relaxed assumption. So we assume that there exists the gain k, here should be tilde, sorry, this is the typo, exists gain k tilde such that the following linear algebraic equation, which solves the following linear algebraic equation. So we need to find k tilde which satisfies this algebraic condition. In fact, if this classical assumption holds, then of course k tilde always exists. You can just select it like before, make this term zero. In fact, in general case, it is not necessary to make this term zero matrix, because then we need a bit less restrictive condition. So after multiplication of this matrix by some projector, we will have zero. In fact, this assumption together with additional assumption about the matrix dependent on this k0 and the control inputs for the output variable, this pair is controllable. So this assumption, in fact, means that the output of which we are going to stabilize in finite time to guarantee the sliding mode has to be completely controllable. It means we can design all uncontrollable variables which affects the output completely. So our control may reject them. So we can see this in the analysis of the dynamics. So here I just compare the structure of the unit control and the modified unit control. For unit control, we immediately have the gain which rejects, which makes this matrix 0, which rejects the dynamics, and linear dynamics, sorry. And when we will compute the dynamics of the output, you will see what the first term in front of sigma, the matrix in front of sigma is just 0. So with this term, unit control homogenize the output dynamics in the sense of standard dilation. And next, we add additional term, which is, in fact, unit control is homogeneous, standard homogeneous of degree -1 as a function. But as a vector field, of degree 0 is a function, but as a vector field, it has degree -1. So this is the classical unit control is based on standard dilation, and but the ideas are the same. First, rejection of the linear dynamics, and next, homogeneous control design. For the modified unit control, we have this rejection of linear dynamics, but this is a rejection of linear dynamics, in fact, related with uncontrollable variables. So after computation of the dynamics of the output, we will have the following equation. And here is just as before, but here we just added and subtracted the same term, CB K tilde and minus CB K tilde multiplied by X. So it is the same dynamic. And with such assumption, we can rewrite our output dynamics in the form of some part of the dynamics dependent only on sigma, and some part which is dependent only on on U tilde, which is controller which we are going to design. So this term rejects all variables which are not controllable, which are not sigma, all the rest state of the X. And now the pair AB controllable, we have the same problem as before. We just need to design a homogeneous stabilizer for the output. And the design is will develop. You can find it in the previous references. Here I just explain with more details how to reject the perturbation of the given gamma, magnitude gamma. So we repeat next the design of the unit control, but using generalized homogeneity. We select some linear part of our homogeneous stabilizer which homogenize the system. So next, A sigma plus B sigma K0 will be nilpotent matrix. And the second part is the unit control. You see, this is a unit vector in the sense of standard dilation, but this one is just a unit vector in the sense of linear dilation. So this is a projector to the unit sphere. It's just by definition of our canonical homogeneous norm, it was defined by such a projection. It was defined such that this norm equals 1. So this value obtained by the definition of the canonical homogeneous norm. And next, for the analysis, we use the same type of Lyapunov function, but up to the type of homogeneity we have. So instead of standard Lyapunov function for the linear system, like quadratic Lyapunov function, or the Euclidean norm, weighted Euclidean norm is equivalent to quadratic Lyapunov function as a Lyapunov. We use the Lyapunov function based on this canonical. So the design procedure is formulated in this theorem. So we solve some algebraic equation. This solution is required to define the gain K0, which homogenize our linear part of the output dynamics. And next we solve in our algebraic system, which is algebraic equation plus LMI, which is required to design the gain K for the control. This is our gain K for the control. And this K and K is designed dependently on the magnitude of the perturbation gamma. So this estimation of the norm of the gamma simply appears in the LMI we need to solve. And this system is always feasible under the given assumption about controllability of A sigma and B sigma is proven. And this lemma is also feasible, and the proof can be based also on our previous constructions, just with some small tricks, but it's also possible to prove that under the same assumption about controllability of A sigma, B sigma, this lemma is also feasible. So we can always design a homogeneous unit control which will reject the bounded matched perturbation, and we can also estimate the settling time to the sliding surface. So based on the value of the canonical homogeneous norm in the initial state and this parameter rho, which is a tuning parameter for the convergence rate. If you want to boost the convergence, you can see that you need to increase rho. In this case, faster you will reach the sliding surface. The analysis, I don't have a lot of time to explain this, but the analysis is rather simple. So the main proof is just a computation of the Lyapunov function for the system. We take our canonical homogeneous norm, we use the formula about its derivative, I showed this them, and we substitute dynamics of the output for the closed loop system, and we have, this is a form the substitution. Since we have homogeneity, this matrix commutes with D. We can put it here. Multiplication D by B gives us just this norm to the power minus 1. It cancels this term. So after using homogeneity, we just obtain, in fact, for the first part without perturbation, we just obtain a fraction of two quadratic forms. So if I will use the notation Z is like this, the first term, which is independent on perturbation, is just a fraction of one quadratic term divided by another quadratic term. But if you see, if x and y are defined from this algebraic equation, then this fraction gives us just a constant minus rho. So this just identically equals to minus rho. For the second part, with the perturbation, we use the usual analysis and some estimates for gamma, just adding, subtracting some terms. We can obtain we obtain the following estimates. Sorry, I did small mistakes in the explanation, because if we don't have a perturbation, if this gamma bar equals 0, then we have just term minus rho. But if gamma bar is non-zero, we will have two additional terms, this one and this one from this fraction. And these two terms will dominate the term which is perturbed, and we will have minus. Sorry. Okay, so the proof is rather simple. It is based on the quadratic, similar to analysis based on quadratic. So here is a design algorithm. Everything is linear and simple. First step, we solve this algebraic equation, of course, based on the selected sliding surface. This algebraic equation, if it doesn't have a solution, it means that our approach is not appropriate for, unit control design present here is not appropriate for this selection of the sliding surface. The previous approach also not appropriate because, as I said, this condition always works in the classical case. So next we check the controllability of this pair. If the output is controllable, then we can design our control. So in fact, the controllability is necessary for our design output, but it is necessary also for sliding mode design, so we cannot avoid it, right? Next, we solve algebraic equation, which is always feasible if the pair A sigma B sigma is controllable, in order to find the gain K0 which homogenizes the system, and in fact also it defines the dilation. Probably I forget to mention, but the solution of this algebraic equation is the solution with respect to parameters G0, Y0, and Y0 gives us K0 after some multiplication, but G0 gives us a dilation utilized for the definition of the canonical homogeneous norm and the control, etc. And the final step, we solve again some linear system to find the appropriate gain and define the control. All this is realized in the toolbox in MATLAB. You can download and play with it just for the design, how to solve, how to find these parameters and next implement the control. Here is just a small example. I've selected some system which has two uncontrollable components. It's just a harmonic oscillator for the first two components, but these two components, they're not controllable, but they affect the analysis part of the system, in our three components for these elements. But the output is completely controllable, and selecting the sliding surface in the following way. So we want just to stabilize only three components which are controllable. But using only two inputs, the standard unit control is not applicable in this case, because matrix BC is not even square to be inverted. Our assumption about existence of the matrix K tilde is fulfilled. We just solve algebraic equation and find K tilde in this form. A sigma B sigma is the output dynamics of the system, which defines our output dynamics of the system are controllable, is a controllable pair, and we can design our controller based on the steps of the algorithms I explained. Here is just some values for the matrices founded from the algebraic equation of algebraic systems, because one is equation and now one is equation plus inequality of the algebraic system. We define the controller based on these solutions. It has some linear part dependent on whole state, some linear part which homogenizes the output dynamics, which depend only on sigma, and the unit control. Similarly to the classical case, we can use the usual tricks for chattering attenuation by replacing some norm with some saturation of this norm close to zero, to have some linear control close to zero, and to avoid discontinuity and some chattering. It's a usual trick for the chattering attenuation in the sliding mode control theory. Here I give just a reference to the book of Professor Roorkee, where you can find these tricks, but I think everybody working with sliding mode knows this trick for practical implementation. Results of simulations without chattering attenuation, with chattering attenuation. So we have two components of the state which are not controllable, and we continue like a harmonic oscillator all the time, but there exists a part which is controllable and stabilize it at a finite time and reject the perturbation of the bounded magnitudes. In fact, that's all what I wanted to present. So, and we have some questions. So here is just summary. So I did this small modification, present a small modification of the standard unit control design methodology. Instead of standard dilation, I use generalized dilation. And this trick allows to relax the very conservative restrictions of the unit control design. And you can try all this in some toolbox which is available in GitLab of our institution, GitLab Andrey. Here is a link. Thank you for your attention.
Long live India and France friendship.